Karun.
Thank you. Can you hear me? Oh, you can hear me now. Thank you for that introduction. These lights are quite powerful. Just give me a second to get adjusted to them. Um, and as Meenakshi said in the morning, this does, like from this view, this totally looks like someone's wedding reception. So let's get started. So actually, I need the clicker. Just give me a sec. So let's begin with with a story about our client's journey. Uh, so the project I'm going to be talking about today is one where we worked with a credit card company, one of the largest in North America, and they originally hired us to come in and do something different. Their entire business was based around credit cards, but they wanted to diversify their portfolio. And to do so, what they wanted to do is launch a brand new product. So they wanted to provide an offering for consumer loans. For this, they got ThoughtWorks in around 4.5 years ago, and I was lucky enough to work on this platform. We spent around 18 odd months, and the platform went live. The clients loved it. We got really good feedback from the end customers as well as the bank. And as the team was trying to figure out what happens next, the bank actually came to us and said, why don't you solve my next biggest problem, which is fraud detection. Most of their revenue at the time was coming in from credit cards. And fraud is a pretty big problem when you're in the credit card space. So let's actually try to understand what credit card fraud looks like. There's three main types of credit card fraud. So the first one is transaction fraud. This is probably the one that you're most familiar with. As you were mentioning earlier, what happens if you actually show up to a point of sale machine? Someone takes your credit card and actually swipes on behalf of you. They just forge your signature as they used to, or let's say they get hold of your PIN these days in India. Well, they can charge your credit card and you're left with footing the bill. This type of fraud is called transaction fraud. The second type of fraud is application fraud, and this is essentially an extension of identity theft. So what someone does here is they actually get hold of some of your documents, pretend to be you, apply for a credit card. And this one's quite dangerous because unlike transaction fraud, where you're at least getting notifications that money is being spent on your name, application fraud means that you don't find out about it for months because the attacker probably changed your address, so they get your bills and you never find out about it. They can spend hundreds of thousands of dollars on your name before you ever find out. And that's a big risk because you're the one whose credit score actually gets affected when they rack up a huge bill on your name. The third type is card not found. And this one's a pretty simple attack. When the credit card gets mailed to you, someone just goes through your mailbox and picks up your credit card. This is primarily the reason why credit card companies, and for that matter even debit cards these days, the bank actually asks you to call in and prove that you've actually received the card by either telling them the number or some sort of challenge phrase after that. That's to avoid credit card not found, this kind of attack. But the one that we were asked to pick up first was application fraud. And there's actually two reasons for it. While transaction fraud is where a lot of money gets lost, transaction fraud has very severe performance requirements. For example, if you're standing at a point of sale machine and you're swiping a credit card, the credit card company gets about 10 milliseconds to actually make a decision on whether something is fraud or not. So when you're building out a new system trying to prove that an idea works, that's probably not the first, that's not the MVP that you want to pick up. Application fraud, on the other hand, you're probably applying online or you're on the phone. You have around 5 to 7 seconds before you have to make a decision. And ideally, you take a lot less time than that. So that's a lot easier in terms of proving capability that you can actually detect fraud in an efficient way, and your accuracy for your model is pretty high. So that's the one we actually decided to pick up first. Let's actually go through what the existing system looked like before we got in. So when you have a customer actually applying for a credit card, let's take the online use case because it's probably the simplest. They'd make a call to our service, to the application service. You have a bunch of forms to go through and you keep filling data out. Whenever the application service feels that it is ready to actually make a decision on whether they would like to give you a credit card or not, the bank takes all of this data and sends it over to a vendor. And this was the primary problem that, this was one of the major problems that the bank was facing. So what happens is that when the call goes out to the vendor, the vendor has full control over how decisions are made. So every time you have a data scientist sitting in the bank making a decision on what the model should look like or how a decision should be made, it took them up to 6 months from them wanting to make a change to it actually being deployed, because that's the amount of time the vendor required to make a change. They had a 6-month release cycle. So you can see, once you're ready to make a change, it still takes you 6 months to deploy a change, and that's pretty expensive for a bank. And especially for something like fraud detection, where patterns change overnight and new attack vectors come up, very, very regularly. This sort of turnaround time is just not feasible. So when the call goes out to the vendor, the first thing they did, they actually did sort of process the entire thing, and they used to return a decision on whether something's fraud or not. And based on this decision, the application service goes ahead and communicates to the customer whether they have a card or they've been pended. And pended is just a fancy word to say, I don't have a decision yet, because you don't want to publicly tell someone that, hey, I think your application's possibly fraudulent, because there's probably additional checks going on in the background at the same time. So let's actually look at how we made a decision on whether something was fraud or not, because that's what we're really here to talk about. And what the vendor did was essentially divide their application up into 3 major sections. The first one is rules. Rules are configurations that the bank provides to this vendor to say, if you see a certain social security number, for example, just flag it as fraud or as pretty high probability for fraud. The reason you do this, again, is because the model takes a very long time to react to the situation and actually learn what it needs to do next. So if you're seeing a pattern that someone's identity has been stolen, and that social security number is being sent to your system repeatedly, rather than having your model react to it, which it won't in time because it doesn't have enough data to react, you just put in a rule to say, if you see this this social security number, just take it to the side and we'll analyze it separately. So that's what rules were used for reacting quickly. And if you think about it, that's really a reaction from the system to say, I can't react fast enough and I need a way to handle the situation. The next important step is the model. And this is where they use machine learning and predictive models to actually determine whether the application looks like it is fraud. And machine learning models are actually used to find patterns in large data sets where patterns are not super obvious to us human beings, right? So when patterns are obvious, you use rules. When they are not, you let a machine decide whether something is possibly fraud or not. The responsibility of a model is to output a score between 0 and 1, which is essentially a probability that, according to the model, how probable does it think that this thing is fraud. So what you do with this output is that you actually send it to you send the score to the strategy. And a strategy is basically a rules engine of sorts, where you're making a decision based on what the value is. Now, if the value from the model is, let's say, 0.9, there's a pretty high probability that it's fraud. If it's 0.1, it's probably okay to go ahead, right? So based on what your business model is, from time to time, the bank actually changes its strategies. And it's not always clean, as in like it's fraud versus not. There's a lot of shades in between. So there are cases where how much amount of effort do we want to take to have a human review this application and like call up the person, verify whether the application is real or not. So higher scores get more time spent on them, lower scores get lesser time spent on them. And if you have an absolutely low score, then you probably get the green light from the beginning. So that's what the current state of the system kind of looked like. They had this sort of 3-tier strategy to handle sort of application fraud, or most of the fraud that they were trying to detect. Let's look at what we actually propose next, because it's similar, but one of the major challenges here, like I said, was the amount of time the vendor took to react to a change. So the hope from the client was, can you help me make can you help me make my models better? Can you bring in a data scientist to help improve that process? But B, even if the data scientist actually makes the model, that doesn't actually help us because it will be 6 months before it actually gets deployed. Can you also make that process quicker? And C, which was sort of one of the secret slightly understated requirements, but they also kind of wanted to bring this business in. It didn't make sense for them to give their client data to another vendor, have them improve their systems, and actually sell this product to other banks, because that's what the vendor was doing. It made sense from a cost perspective and an intellectual property perspective to actually bring this business in-house, which is a trend that you'll see in a lot of industries right now. So the hope was that we can help change this, and what we ended up coming up with is the concept of challenger models. So when a data scientist sitting in the bank comes up with an idea, the idea was that we'll help them build this model and deploy it really, really quickly to production. And in the beginning, this model might not be ready. It's not proven to be battle tested. So why don't we let it sit on the side? So when an application comes in, let it go ahead and go to the vendor. The vendor system, which is still sort of the source of truth, takes a decision on whether something is fraud or not. But at the same time, we're sending the same data to all of our models, and we want to gather feedback, right? Trying to get feedback as early as possible with real-life cases helps make our model better. And the data scientists are on top of this, making sure that the model is doing what they think it should, and actually getting data. But in the meanwhile, the model still sort of the vendor is still responsible for making the final decision, which is whether something's fraud or not. So the next thing, so after this period is done and we feel comfortable that we have a model which actually works and is more effective than the model that the vendor had, the next step is to actually take the model out of the vendor system, or rather just stop relying on it, and then promote one of our models to what we call as the champion mode. Now, we didn't call it promoting it to production because challenger models are technically deployed on production as well, but it's essentially sitting there and not making decisions, whereas the champion model actually affects customers. It makes real decisions. It impacts your life as an applicant who's trying to get a credit card. And what this allows you to do, as you can imagine, is when a customer application comes in, now you still make a call out to the vendor to make sure that the rules get executed, because that's the first step. When the response comes back, instead of running the models which are also on the vendor, we now start calling the champion model, which actually makes the real life decision. The challenger models are still run in the background just to get more data and improve them, but the champion model responds with the data, with the decision. We go to the strategies engine because the model only spits out a score. Somebody has to take a decision on whether this is fraud or not, and the strategies part actually helps us do that. The response comes back. We get the green light, to respond to the customer, and we go ahead and do that. And as you can see, this model is a bit complicated. We've added a lot more steps than we had initially. And if you think about why this happens, this is because now we split the responsibility. Earlier, we had the rules, models and strategies all in one place, but we've actually split that up into a separate system. We weren't the only ones who were trying to tackle this problem. We were trying to bring the models into the bank, whereas there were other teams at the same time trying to work, they were working on getting the rules and the strategies in-house, so that they had that capability to actually completely replace what the vendor was providing and actually make quicker changes to their system, which is what they wanted from the beginning. So let's talk about what fraud detection actually looks like. I know I briefly touched on it, but let's try visualizing it, visualizing what the output of a model actually looks like. So if I build a graph, on the x-axis you see model scores between 0 and 1, and on the y-axis you have application count. If you plot all of the not fraud cases, where you know that the application was legit, there was a real human being who was applying, you'll see most of them are concentrated on the left. And now if the model was perfect, you'd probably just see a rectangular box and there would be nothing on the right-hand side. But since nothing in real life is perfect, you do see some non-fraud applications which are also on the right-hand side, and this is just how life is. Now, if I also plot the fraudulent cases, as you'd expect, they're more heavier on the right-hand side of the graph, which means that you have more fraud cases having higher model scores. So that's kind of the way we designed the model in the first place. Now the interesting thing is, how do you make a decision on what is and isn't fraud? Now this process is called thresholding. You can arbitrarily draw a line anywhere on this graph, and that anything to the right can be fraud versus anything on the left won't be fraud. Just for the sake of discussion, let's say we draw the line right down the middle, which is at 0.5. If we do that, we notice two interesting things. One, there's a section that I just highlighted at the bottom. These are false positives. And what that means is these are cases which are not actually fraud. They are real people like you and me who are trying to get a credit card. But unfortunately, because of some patterns or some of the data that we've entered during our application, the model ends up thinking that these are fraudulent cases, right? Essentially, what has ended up happening is if this goes unchecked, real people who could have been using your product, we would end up denying them, and that's something that you don't want. In an ideal world, you'd have 0 false positives. But more interestingly, you also have something similar on the left-hand side. You see false negatives, and what that means is there are cases that we thought were not fraud when they really were. And now you're starting to see the problem is irrespective of where you cut a line, because the models aren't absolutely perfect, and in real life they almost never are, you will always have this gradient where there will be false positives and false negatives. And if you sort of go back to class 8 or something, where we looked at mathematical functions and we used to draw graphs to plot sort of cost value benefit, well, that's what we're about to come to. All of that math in 8th standard is now about to pay off. So how do we actually minimize the amount of losses is what we will look at next. So there is a formula called as loss profitability that they look at. And it's pretty, it might sound complicated, but it's pretty simple. So if you have a dollar value to fraud cost, which is essentially how much money do I lose when I have a fraudulent case, right? And if I multiply that by the number of people I accidentally let through, I mean, they were fraud cases, but I let them through because I made a mistake, right? If you multiply these two items and then add to it the product of opportunity cost times false positives, which is opportunity cost is the amount of money you would have made when the customer is legitimate, the possibility of making that money, but you didn't because you actually turned them down, by the probability of you turning someone down even though it was a legit application. If you add these two numbers up, you essentially get a sort of dollar figure as to how you're losing money. And so the point is, and where this ties back to sort of that 8th standard math of drawing graphs and trying to find out where lines intersect, is you can actually plot these on a graph and you will see an area at which the amount of loss is minimal. And that's sort of your sweet spot. And that's how data scientists figure out where to threshold, right? Like in the earlier diagram, we just drew it down the middle just because it seemed easy. But in real life, that decision is very, very hard and very important to your business. You want to minimize the amount of loss that you have, and this formula actually helps you make that decision. So now that we've looked at, just how overall we try to think of this problem, let's look at how a model is actually trained. And I'm going to give you a brief introduction into the concept of supervised learning. So the first thing we do is that we actually pick up historical data. Now, since we're at a bank, they have data on everything, right? And sorry, on the earlier slide, the numbers that we talked about, since we were at a bank, it's a data-driven org, it was pretty easy for us to get dollar values because that's what they do. They calculate opportunity cost, they know the amount of fraud loss, right? So it's pretty easy for us to calculate that. So we take those numbers and all of the applications that they've ever had, which is 10 to 15 years of data, and actually collect all of it and use that and split that information into two parts. About 70 to 80% of that data is what we took as training data. So we used it and applied algorithms on it to come up with a model. And a model is the thing which produces that score. But the remaining 20 to 30% of data that we didn't actually use for training the model, we used for testing. So, if you show the model all of the data, guess what? When you test it against the same data, it's going to be great at predicting fraud. You will have a very high accuracy rate. But the real interesting thing is for you to, train it on a certain set of data, and so you give it basically, all of the application fields as well as the actual decision, whether it was fraud or not. But when you test it, you hide the right-hand side, the answer, and you ask it to predict the answer. And you evaluate it, just like we evaluate students in school. We evaluate the model on its ability to give correct answers and how accurate it is. So models usually split out based on the kind of classification you want to do and the algorithms you've used. They spit out answers. In our case, we use something called as binomial classification. And what this means is the model will spit out two answers, in our case, whether it's fraud or not fraud. So you could also use a multinomial classification, and you could have more decisions that you can bake in here. But in our case, the model only required two decisions. Now the question to ask, like I mentioned, building a model is, there are frameworks which actually give you all of the algorithms almost ready to use, as long as you know how to configure them. And it's only a couple of lines of code to actually produce a model. And as a fake data scientist, it is pretty easy for me to say that, oh, it's just 5 lines of code, anyone can do it. So what do data scientists actually do, right? They have a very, very critical role. And the point isn't just how you configure something to get the model. It's really about how you treat the data and how you make sure the data is something that the model can understand. And in this entire process, that is probably the single most important thing that has to be done. Here are some of the techniques that data scientists use to actually filter the data. So, to make the data, to prep the data in a way where the model can actually understand it and derive real value. The first one is data filtering. So let's talk about cardinality. Now, cardinality is a concept which kind of explains how many instances of a certain data you have in that column. For example, if you look at application type, in this sample data, everything's a credit card application. You know why? Because we work for a credit card company. All applications will have the same type. Having low cardinality is not really useful to the model because it has no correlation. Clearly, it has no correlation on the fraud status. So you want to avoid low cardinality items. But at the same time, you want to avoid high cardinality items. Things like names, because it can cause two problems. First, first name and last name together doesn't really give you an indication towards fraud. There are just far too many combinations of those names. So the model won't be great at predicting it. And if you use high cardinality items like this, what ends up happening is the model becomes overfit. And this is a phrase that you might have heard. And what it means is essentially the model is ready to detect exactly this data. But when you actually introduce the model to the real world, guess what? It's pretty bad at recognizing what you want it to. There are famous cases of overfitting where the test data wasn't appropriate. And they're pretty funny cases. I do recommend, if you like stories like that, there's a very nice talk that I forget the name of the speaker, but she gave at Strange Loop 2018 this year about problems that machine learning systems actually have. And it's just hilarious stories about how machine learning has failed because we've made mistakes. If you're interested, just let me know. I can send that talk out. It's a good thing to listen to for like 30 or 40 minutes. It's absolutely worth your time. So what you really want out of your data set is medium cardinality, a finite number of possible values, so that your model can actually try to predict the correlation between the answer and the data point. So something like submission method is a good example because there's usually only 5 or 6 ways to actually submit your application. I mean, I'm not trying to predict, imply that web applications are are always fraudulent, but that's just an example of how you can draw this correlation. The next thing you can look at is data transformation. Now, if you take emails again, it's kind of obvious that emails are a very high cardinality item. Emails are pretty unique in your data set. But if you actually do a small transformation, like dropping out the actual the first part of the email address, which pertains to you, and actually looking at the domain name, you've transformed this data. And what ends up happening is that you've actually reduced the amount of cardinality. Now suddenly the model can look at patterns and realize, oh, if your email probably comes from has a domain of @fraudster.com, there's a high probability that there might be fraud. I don't know why we needed a model to tell us that, but oh well. The next kind of thing that we do is data imputation. And this is a slightly tricky one. And this is where, in my opinion, like data scientists do things which just us mere mortals, like it's hard for people like us to do. This is very, very time consuming. So what happens when you have missing data? The usual answer is, I could just leave it there. But guess what? The blank field then becomes a value, right? And it becomes a value that the model trains on. And then the model is inaccurate because it makes a relationship between values being absent and the status of the model. That's not really what you want. So if you take a column like applied before, which has a Boolean value, you could use a strategy like giving it a default value. But you have to be very careful because if you have enough null values in that column, guess what? Now you putting a default value in actually biases the model a certain way. So this is where the intuition, the knowledge of a data scientist actually helps in knowing whether this works. And some of it is based on tests. So they make a change, they actually check what happens to the model, test the model whether it works or not, and do this again and again and again. Right? And that's where, as I said, like data scientists do something that like people like me are just not geared to do as well. So the next thing, another example is a salary column. And obviously there is no default value to salary, as much as some people would like that, or maybe not like it to happen. So a common strategy is to maybe use an average or a median. But again, be careful about what this does on your actual system itself. So another example is of a thing that data scientists usually do is feature selection. Now, if you take zip codes, a very high cardinality item, maybe it gives you some correlation, but cardinality is pretty high, so predictability, accuracy of your model will be not that high. IP addresses are the same way. But if you actually use the two, derive a correlation and come up with proximity, which is essentially a distance between where you applied from and where you apparently live, for most use cases, we notice that the distance has a pretty high relationship. So the row 2 on this, you can notice that the zip code was in Sydney, the IP address was in Chicago, and this was fraud. So if the distance is above a certain threshold, it learns to notice that that there's a high probability that something is fraud. And this is actually a real life use case. Ironically, while we were in the US, like I was in the US while doing this, and we, ThoughtWorks in the US, like all of us are traveling consultants. So quite often we would apply for credit cards sitting in, let's say, San Francisco, whereas our home address is New York. So we found this funny that most thought workers, by using feature selection like this, we would actually probably get our credit card applications not going forward as quickly. But hey, we are the 1% or something, so it's not as much of a big deal in the large scheme of things. So now that we've looked at what data scientists actually do, let's look at the architecture of the solution so we understand how we're actually trying to make our customers' lives better. So we divide the application into two sections, the data scientist workflow and the developer workflows, because there are essentially two actors to the system, at least in the beginning. Let's first focus on the data scientist workflow, where you take raw data, you transform it, as we talked about, you use all of the techniques, and you actually create a trained model. And in the developer workflow, we have 3 more steps where we take the trained model, we build an application, test it again, and then produce a score. Let's go through the data scientist workflow in a bit more detail and see what that actually looks like. So as I said, the first step is to actually take the raw data. So we take the historical data store that was provided to us by the client. We go through the cleaning techniques and all of the other sort of data prep techniques that we talked about, and we actually use the language which actually made sense for the data scientists to work on. At the client side, this meant using Python, which is a new thing at the bank, but we actually got all of the approvals to actually use a new language, and we were able to do this. So the next step is, after this is done, we take the output, the clean data, along with the configuration for the model, also done in Python, a language which is very friendly for the data scientists we had at hand, and gave it to a framework called H2O, which is responsible, which has implementations for the standard model algorithms. So the data scientists could actually pick and choose, try different things out, and the whole point of this project was kind of experimentation to figure out what the best model is and get really quick feedback, and H2O allowed us to do that. What H2O does with that configuration and that data set once it trains the model is it produces a Java code, a Java class. If you want to read it, you can try to do so, but it's going to be thousands of lines of if conditions. Good luck reading that, but we were actually asked by someone to set up a review for that file, and it was a lot of fun. Like every other Java piece of code, what we do is we compile it, we package it, we put it into a jar, and eventually upload it to an artifact repository, such as Artifactory or Nexus, whatever is available in your client location. And this sort of completes the data scientist workflow. We gave them something which sets up their machine, makes it easy for them to set up the data in the right way and produce a model very, very quickly using single commands. All of the tools that we as developers kind of rely on a day-to-day basis, but for data scientists, this is a game changer because they're not used to such tool sets. They're not even used to something like version control. So there was a bit of sort of onboarding that we had to do to sort of get them used to this this whole ideology. But this is where it was great for us to actually pair with the data scientists because we could actually bring sort of the best of both worlds. Data scientists with their deep knowledge on how to actually train models, and developers with sort of their CD background to actually automate a lot of this work. So as you notice, we went from raw data to trained model. And what we're going to look at next is probably what we did on sort of the developer side, whenever the slideshow decides to catch up to me, because I screwed up the transition. Okay, so next let's look at the developer workflow. So here, the idea, this kind of picks up from exactly where we left off. The data scientist made sure that ran the command and checked stuff in after they're ready. The pipeline actually built a model and pushed it to an environment. Well, once that happens, our pipeline kind of triggers the next step, which is it takes the model from the jar, and us developers, we built sort of a shell project, which allowed us to, using artifact versioning tool. In our case, we used Gradle. We actually pointed towards a certain version and said this one needs to be ready to go to prod. Right? A one-line change, just add the right version number in, and you're good to go. Well, what this meant was now you've service enabled the model. A model used to be just a Java class. If you call the right method, it spits out a score. But by doing so, we were able to produce a HTTP service with a simple endpoint, which allowed us to use it in our workflow. So we used something called a Spark Java as a framework for this. Please do not confuse this with Apache Spark, completely different thing. It's kind of like Spring Boot, only a lot smaller, none of the DI stuff. We call it Tornado to make it HTTP enabled. What we did here, because we sort of worked with the data scientists where they wrote all of their code in Python, we built a pipeline such that all of the data munging techniques or data cleanup techniques that they have actually get pushed into this service. So as the actual request comes in, we have to make sure the data gets prepped in the right way and it's formatted and cleaned up in the right way. All of that is done inside the data analytics platform. We take that message and actually push it onto a simple message queue. And the reason we do this is so that all of the models can work in parallel and we can scale horizontally. So you can have hundreds, if not thousands of models running, and there is absolutely no effect on what the customer sees. So in the beginning, while the real model is still working, we have data being captured in shadow mode. Models can then start responding, push messages to the queue, which the data analytics platform picks up. What we do with this is we then go to a model predictions repository, store all of this information. And the reason we did this is we can build graphs on top of it. So we built a dashboard which helped people visualize in real time how effective a certain model is based on different parameters that data scientists need to make this decision. And whenever they thought something was ready, they could actually use these graphs to actually know whether a model is ready to be promoted or not. Well, once shadow mode is complete and we feel comfortable with something working, we went ahead, we removed the model from the vendor side, we promoted a model to champion mode, the request came in, the rules got executed, response came back, the decision analytics platform got called, and this time our champion model makes the real decision. There is no vendor model. The model actually responds, but at the same time we're putting a message on the queue so that all of the other models can run in parallel to continue to get that feedback. So you don't just have one model sitting on production, you have 20 of them. or competing with one another in a Hunger Game style mode to actually try to, become the champion model. The responses come back, and the customer, you go back to the vendor, you take care of the strategies and stuff, and then go back to the customer. But in the meanwhile, like I said, your shadow mode models still work. They still gather data, and your models repository, your predictions repository actually has information on how effective models are. So this is how we went from applications to actually getting a score and making a decision. So this is what our production environment actually looked like. So we went from a data scientist desktop all the way to prod really, really quickly to help deploy their models and get feedback quicker. So the next thing that we need to be doing is, now that we've seen sort of the two aspects of the application, let's actually look at the value stream really, really quickly to try to understand what, how this tied together. What does the end-to-end state look like? How do we actually get value out of this, and how does the customer actually get what they want? Well, step one, like we said, was data ingestion. We cleaned up a lot of that data. We trained the model. Another thing we did during this training was the training process actually spit out a lot of reports. Reports which were useful to understand from a data scientist perspective, the hard numbers on whether a model that we've trained on training data, whether we think it's efficient or not. Well, the reason why we build these reports is because, if you work at a bank, you have governance teams. And governance teams are really responsible to make sure that that you're not doing the wrong thing. There are a lot of rules on to make sure that you're not discriminating against your customers. And this is the team which is legally responsible to make sure that that doesn't happen, right? So they are very, very important, and they have to sign off on a model before it gets published. But once it gets published, we use continuous delivery mechanisms. So when they approve it on the pipeline, it gets published automatically. We go ahead, make sure all of the rest of it is automated. We publish a service, and then we take it all the way to prod. There is no hindrance in this, go straight through. And then we come to what we call as shadow mode. Well, once something is in shadow mode, the next obvious thing that we need to do is governance evaluation. Well, the reason why this governance is different from the one that we talked about on the top is because here, well, we're looking at really making a decision on whether the first governance was on training data. So we wanted to do a pre-check to make sure that we're not discriminating. Well, guess what? The later governance is actually on real production data. So they let the system soak in for a while, get those statistics in, enough applications have been processed. They then approve a model to go ahead. And when that happens, we get what is called as a champion model, right? So if you look at this entire value stream, what you will notice is that, while the talk was about fraud and how we help, quickly, we helped data scientists deliver more models to prod and actually reduce the amount of fraud, by the way, which we were pretty effective in the amount. So the model effectiveness for the vendor was around 76%. Ours was around 92 to 93. So there was a pretty significant jump in the model itself. But that's not the real success story. I mean, sure, the business loves that they saved a ton of money, because they have essentially, for fraud, they have a bunch of money kept on the side to sort of take out from. They're ready to lose money, and they've sort of given up to that fact. But by making these models more effective, you've essentially allowed them to save a lot of money, which can go into feature development, which can go into actually giving their customers more value. But that's not the only thing. If you look at this entire value stream, you will notice there is nothing fraud specific about it. In fact, there is barely anything specific to even a bank. This is a pitch to talk about how you can use continuous delivery and various testing styles, which I didn't get the time to actually go through. But how do you use all of that to deliver a model to production, make the best of both the worlds, the developer as well as the data scientist, to actually do what we always do on our day-to-day projects, which is build models really, really quickly, test them out, get feedback continuously, and deliver value to production in a very short amount of time. So just as a last statistic that I'd like to leave you with, when we walked in, the initial process between a data scientist thinking of an idea that they want to do, like just experiment with something, to actually deploying it to prod and making it real was 3 years. At the end of this project, minus the governance times, it took a few minutes. While this might sound I mean, I know I'm in a room of technologists who eat and breathe continuous delivery every day. This is not surprising for us. But when we've done these talks around the world for data scientists, this is a game changer for them, right? And for us, this is obvious. This is primarily the reason why I want all of us to pair across roles, because you can bring in different aspects from your different disciplines, and that is how we go to the next level. With that, I'd like to thank all of you. My name is Karun Japhet, and if you have any, I think we might have a minute or two for 2 minutes for questions, so I can take a couple. Yes. Sorry, I can't hear that. Just give me a sec. I think we need a mic.
So I have this question about
Or you can just come ahead. That's fine with me as well. I'll repeat
Hello?
the question for everyone else in the room. Maybe you can just yell the question out. No? Oh, there we go. Nope. Technical difficulties are a part of being at a tech
So I have
organization.
this question about training the model. You said when you are training the model, you'll need to do some manual work to filter the data and to do all these things, right? And that would be the difficulty in automating that process, because generally when you put models into the machine learning things, there are things like you want to continuously improve your model as well with respect to newly coming data. Like in last 10 years, this is the trend that has happened, which has trained that model for that last 10 years data. In upcoming 10 years, there might be some different trend which that model wants to acquire to, right? So was that the only difficulty of the filtering and all those challenges to automate that process as well?
Right. So the point of the machine learning, like the reason why we use machine learning to build those models, is we don't know what the patterns are, right? Like you rightly pointed out, the difficulty is knowing that. The data scientist's role is to know how to get the data ready, get it in a state such that the computer can understand it. That's it. It's kind of like what we do as programmers. Like we have a requirement. We're the people who actually tell a computer on how to actually do that job. We write code for that, right? So data scientists are kind of choosing the right algorithm for the right problem, making sure the data is set up correctly. What they're not doing is telling the model that this is an important feature that you should look at, right? Sometimes they do that with certain biasing for certain features, but most of the time they're not doing that. They're letting the model decide what actually works. And this is a time-consuming process where they train the model, they test the model, and they keep going in that sort of loop to keep improving the model. So every time they think they have a release candidate, then they put it to production to actually get more feedback. But it's all about feedback for them. They have to keep doing this again and again to make sure the model does something correctly. But sometimes they notice, the only times they actually manually make sure the model knows that they have a preference is when is through something called as weighting, as in WEIGHTING, putting weights to a certain thing. So the idea is that they make sure that if a certain model, if they notice that if you take a certain column out, the score changes dramatically, they will put a high or a low weight to it, to bias the model in a certain way. But that biasing is super important for governance. They do watch that very, very carefully. Okay?
I think we can take
Thank
other
you, everyone.
questions offline if possible. We are running out of time. Very sorry.
Thanks, everyone.
Hello.